Hello everyone, my name is Andrew Marin, and I first want to thank you all today for stopping by my virtual walkthrough of my poster entitled Multisensory Expectations About Dynamic Visual Objects Facilitates Early Sensory Processing of Congruent Sounds. In everyday life, visual objects are often accompanied by sounds, yet little is known about how these two sensory streams influence each other. Past research has examined the brain's response to static audiovisual low-level and dynamic high-level social stimuli by measuring event-related potentials, or ERPs. For this study, we asked how do expectations about dynamically moving objects influence early sensory processing of sounds. Specifically, we examined how dynamic visual input, like an object moving continuously across the visual field, influences early auditory processing of sound that is either congruent with the object's motion, and thus likely perceived as being part of the visual object, or incongruent with the object's motion. With that in mind, we had two specific hypotheses. First, audiovisual temporal synchrony will result in an efficient auditory ERP response characterized by a decrease in peak amplitude, faster peak latency. Second, audiovisual temporal asynchrony will result in an inefficient auditory ERP response characterized by an increase in peak amplitude and slower peak latency. So 31 college-age neurotypical adults participated in this experiment. Below is a single trial depicting the synchronous condition through time. For each presentation, a small achromatic fractal video was first presented to promote participant engagement during the passive viewing task. The task was passive viewing because we were interested in integration independent of tasks. A small fixation cross then appeared, followed by the random presentation of 1 of 4 sensory conditions for a total of 416 experimental trials, 104 trials per condition. The interval here contained the primary task where participants were asked to view a ball that moved from the left or the right and may or may not be presented with auditory input. Upon completion of the event stimuli, each participant was instructed to identify a single target letter amongst 7 distractor letters, which served as an attention check. I want to show you what the participants saw during the paradigm. Here is the visual presentation, where it contains a continuous motion of the ball, no auditory input. Here's the asynchronous presentation, where the sound occurs before contact with the wall. And here's the audio-only presentation, where it contains the auditory input, but no continuous motion of the ball. And lastly, the synchronous presentation, where the sound occurs precisely when the ball contacts the wall. I'll now present the 4 left start sensory conditions with an event epoch drawn below. The red frame here reflects the point in time in which we're event epoching for each sensory condition. Here are the brief descriptions of each trial, which occurred with equal probability and was randomly generated. Moving on to the ERP analysis, where we assess the N1P2 auditory response within the red frontal central region using high-density EEG, where we conducted a within subjects repeated measures of NOVA for each sensory component's peak amplitude and latency responses within these color-coded time windows pictured here. I'll now present the grand average ERPs for 31 adults. On the y-axis reflects voltage, which is plotted positive up, and the x-axis is time in milliseconds. These ERPs reflect the main effective sensory condition over the frontal central electrode sites. And these color schemes of each condition will stay consistent as I now walk you through the significant results of sensory condition of each component. I would like to point out that the visual-only condition was omitted from our NOVA models due to a non-discernible ERP. For the N1 peak amplitude and latency responses, this figure here, where the y-axis reflects voltage in microvolts and the x-axis reflects sensory condition, presents individual level scatter plots that are color-coded by sensory condition. Overall, N1 minimum peak amplitude was significantly smaller for the synchronous condition compared to the audio-alone and asynchronous conditions. Meanwhile, N1 minimum peak latency, where the y-axis is latency in milliseconds, was slower towards asynchrony compared to the audio-alone and synchronous conditions. The synchronous condition was also faster compared to the audio-alone. And this is consistent with the interpretation that synchronous events are processed with greater efficiency. And conversely, asynchronous stimulation exhibited inefficiencies within the slower peak latencies and higher peak amplitude responses, and they were present at the N1, which suggests some early perceptual sensitivity toward dynamic audiovisual input. And finally, the P2 response for the amplitude and latency. Overall, P2 maximum peak amplitude was smaller for both multisensory presentations compared to audio alone. Effects of latency found that the asynchronous condition exhibited slower P2 peak latency compared to the synchronous and audio-only conditions. And overall sensitivity towards asynchronous events still manifests within this later P2 auditory component. In summary, these findings suggest audiovisual synchrony elicited a faster and attenuated early auditory response relative to asynchrony or auditory-only events. To conclude, early auditory ERPs are sensitive to the temporal relationship between audiovisual inputs. And these patterns of results suggest to us that efficient sensory processing is elicited when auditory input is either congruent with the object's motion. Secondly, inefficient sensory processing occurs when auditory input is incongruent with the object's motion. This suggests that visually induced expectations about a stimulus may alter the brain's allocation of known resources and other modalities. And finally, ongoing research in the lab will look to examine if continuous visual input is needed to generate the multisensory effects. As an alternative explanation of the findings in experiment 1 could be that the brain was sensitive to the expectation of the synchronous event when given visual motion cues. Specifically, we plan to present participants a new sensory condition depicted here, where subjects will be briefly shown visual and motion cues provided by the ball and its motion, and the ball will eventually become occluded upon synchronous contact with the edge of the display. And finally, here are the references for the poster. I'd also like to thank all the awesome undergraduates that participated and my advisor, Leslie Carver, and fellow collaborator, Störmer, and you for listening. Thank you very much.